We will click to run our model on the virtual hill device. Now a hill SCADA window is shown. From right side, let's define our voltage sources. The first, the second and the third one. We will change the source type and for each of them set RMS value to 230 volts. Also, the phase shift has to be set. Second one will be minus 120 degrees and the third one will be plus 120 degrees. When we have defined the sources, everything is ready to start the simulation. Before we start the simulation, we will make the complete control and observation under the SCADA panel. Let's create new panel. We want to divide the SCADA panel into two groups, so group widgets will be used. We will move and resize them. The name of the first one will be grid. And the name of the second one will be battery storage unit. Into the first group we will add a few gauges which will be used to observe the voltages and the currents in the grid. We would like to observe the RMS voltage AB and the voltage between phases B and C. So let's take two gauges. We will use the first one for the voltage measurement and the second one for the current measurement. We will change the name of the first gauge to VAB. The analog signal which we want to observe will be VAB RMS. Make sure to always change the color from red to white by pressing enter. In the advanced settings tab, I will just change the scale. Current scale is between 0 and 100 and we want to type 500. Apply changes. We can spread this gauge. We will do the same for the other voltage measurement, the one between phases B and C. We can copy this widget and paste it here. We will make some modification. The name will be VBC and the analog signal will be VBC RMS. Press enter and click OK. Now we have got the voltage measurement gauges. We will make this gauge a bit smaller because we will measure the current in all three phases A, B and C. The name will be IA. The analog signal will be IA RMS. Press enter. In the advanced settings tab, we will change the maximum value to 50. Let's click OK. We can duplicate this gauge 2 times. For the second one, we will change the name to IB and the analog signal will be IB RMS. For the third one, the name will be IC. The analog signal will be IC RMS. Let's click OK. That is it. Now below these gauges we will insert a multi-trace graph. With this graph we will observe the power flow in our model. So we will observe power which we measure with the power meter, active and reactive power. Let's double click on it and we will change the name to active and reactive power. In the Advanced Settings tab, we will change the axis. We do not want to be auto scale, we want it to be between -30 and 30. Let's go to Basic Settings tab, and for the data type, we will choose expression. So here we type a Python code and use Typhoon AP. So we will add new variable. We will call it power and it will be equal to hill.read analog signals. And we will open and close parentheses, and between them we will open the Python list with square brackets. The first thing that we want to type here is a string P. It means active power. Then Q. So the first and the second signal that we will observe will be the active and the reactive power. This red signal is few kilowatts, so we want to scale the power and we will add a new variable called power K, and it equals to x divided by 1000 for x in power. We will divide the measurement power by 1000 and make a for loop in Python. It means that values P and Q will be x divided by 1000. Display value is a variable which will be shown on the multi-trace graph. Inside of defined list, we will assign measured values through power K and also add the new list, a new list with the labels that we want to show in the legend. So we will type active power for the first signal and reactive power for the second signal. Make sure that you have opened and closed both lists here. Let's click OK and apply changes. We can run our model to see what is going on inside it. Before, we have to set SCADA input enable to 1. As we can see, we have voltage measurement here, current measurement, and the current active and reactive power, but we still have any control. Let's stop the simulation. Here we would like to add buttons for injecting the harmonics to our grid and to go back to the normal grid. In that case, we will use the button widget. We will take 2 widgets. The first one will be named Grid to Normal. Under the microcode part, Typhoon API commands will be used to saturate the grid's voltage source. Let's click on Edit in Code Editor, find Source Settings. Section Source Type has to be changed to Sine. For every source, we will set wanted values. RMS voltage has to be for all sources 230 volts. Frequency 50 Hz. A phase for the second phase has to be minus 120 degrees. And for the third one, plus 120 degrees. When everything is set, we have to insert 3 code lines. Now, when we have typed everything here, we can save the changes and close the window. For the other button widget, we will use it to add harmonics. We will call it Add Harmonics. And open the API wizard, and we will do the similar as in the previous situation. Actually, we will just check the harmonics checkbox, and we would like to turn on the 5th harmonics for this signal, and for example the 11th. The first one will be 0.1, but take into account that this is per unit value, that is 230 volts multiplied by 0.1, so it means that the 5th harmonics will have the RMS value of 23 volts. And for the 11th harmonics, we will type the same 0.1 and press enter. On the right side, we have a preview of our signal. It is fine, we have added the 5th and 11th harmonics. We can close this window. Now we can simply insert the one code line for phase C, and we can close the API wizard. Here we will add some modifications. We will copy this line and paste it 2 times. The only thing that we want to modify is to change second code line for phase B. Modify phase and add harmonics. The same thing has to be done with phase C. Our harmonics that we have chosen from API wizard are now in the Python list. So, we can even read here that the 5th and the 11th harmonics are 0.1. Let's save this and close. Now we are going to the other group where we will insert a few combo boxes to control our charger. We will add 2 combo boxes. Two LEDs, and below that we will add 2 sliders, and also 2 gauges. We will use the first combo box for a converter to turn the charger on and off. Name of combo box will be changed to converter. We will rename case 1 to on and case 2 to off. Within the Python code, we will change case 1 to on and case 2 to off. Now we can open the API wizard. From the SCADA input section, we will find the enable input. We will remove these 2 lines, comment and pass lines. For the first line, we will type 1 for enable and insert the code line. It means that the enable control will be value 1. For the off state, we want the enable to be 0. Now we can insert this code line and save and close this window. For LED, we can remove the name and we will change the color to green. Digital signals that we will observe will be PWM enable. We will adjust the properties for the other combo box and type the code. It will be called operating mode. The first operating mode will be discharge and the other one will be charge. Now we are going to change the Python code. Above this code we will have to import the numpy library because we will want to use the square function from numpy library. We will type import numpy as np. Also, since this is the operating mode, we will define the global variable which will be used in this slider. Let's type global OP mode. Operation mode will be equal to the input value. Operating OP mode equals to input value. Now we will make some adjustments here. We will change the input value into OP mode. Also, case 1 will be discharge and case 2 will be charge. We will remove this code here and type our code to calculate the ID reference. So I will type ID ref equals to ID num. Nominal value will be 35 amperes, which we will define in the SCADA initialization. We will do this later. Since inum is an RMS value, we will multiply it by square of 2 and multiply by iref. Iref is a value which we will define with the slider, and there it will be a global value. We will copy and paste this line under charge. But we will change the sign to minus. Now our positive power flow, when we are discharging the battery, means that the power flow from the battery to the grid. And our negative reference is when the power flow from the grid to the battery. Now we will apply these values from the SCADA input IDREF. We will open the API wizard. In the SCADA input section, there is the IDREF line, and we will simply insert it here. We will not use 10 for the value, we will use IDREF. We can save this. We can select everything because we will use the same code with some modifications for the slider below. I will close this window. I will double click on the slider, paste this code, and we will set the iref as the global variable. Instead of OP mode, we will type iref equals input value. We will change the minimum and the maximum value. The maximum value will be number 1 and step will be 0.05. The name of the slider will be charge, discharge, current, set point, PU. Everything is defined and we can close this window. As we can see, the charge-discharge slider is moving between 1 and 0. Of course, there is a widget error because we didn't define a few variables within the SCADA initialization. We will use this other slider to control the reference of reactive current. The name will be reactive current set point PU. The minimum value will be minus 0.3 and the maximum value will be plus 0.3. The step will be 0.05. Here we will calculate the IQ-ref value. We have to import NumPy library and also calculate the IQ-ref, which equals inum multiplies by np dot sqrt of 2 multiplied by input value. We will apply this value to the SCADA input IQ-ref. We will open the wizard and insert the line for IQ-ref. We will change value 0.0 to IQ-ref. That is it. We can save and close. We will use this gauge as the voltage measurement. We will observe the voltage of the battery. We will just type VDC and measure this voltage. We will change the name of the gauge into battery voltage. We have to change the scale to between 0 and 750, for example. Applying the changes. We will use the other gauge to observe the state of the charge of the battery. The name will be state of charger. We cannot find the analog signal to observe the state of the charge, so we will use an expression for the data type. Let's lower this line. Here we will define the new variable SOC. SOC will pick up the battery state. We have to type hill.get battery SOC brackets battery. Now, when we read the state of the charge of the battery, the value is between 0 and 1. To display value, we will type display value equals to SOC multiplies by 100. Apply the changes. And we forgot to define the second LED. The name of it will be over voltage. And the digital signal will be over voltage. If the battery is fully charged, the LED will light. Now we will open the SCADA initialization and we have to add the already used values from the combo box and the slider, but we have to type the initial value. For example, OP mode equals to discharge, IREF equals to 0.5, and INOM equals to 35. Let's close this window and change the name of variable in the combo box and first slider from ID num to inum. We will change the operating mode to discharge and start the simulation. Now, as we can see, the battery is discharging at 12 kilowatts. So, if we change the operating mode to charge, the direction of active power flow will be changed, and now it is minus. So it means that the power direction is opposite from this RMS current meter, so the power goes from right to left. Let's change the set point of charge. As we can see, at this multi-trace graph, the power is changing. We can switch to the operating mode discharge, and we can change the reactive current set point. The reactive part can rise or fall. Here we can see that when our battery is discharging, the state of charge is going down, and we can observe the current through all three phases, as well as the line voltage AB to BC. We can turn our converter on and off. The last are the grid to nominal and add harmonics micro buttons. If we click on the add harmonics button, we will see that there is a difference in the currents and the voltages. If we add harmonics, the voltage is higher and even the current is slightly higher. To see much better what is going on with waveform when harmonics are injected, we can use capture scope tool to observe, for example, voltage VA and current IA. Right now, we can see presence of higher harmonics in grid voltage and current.